on the topic of chemical vapor deposition, I thought we could also discuss diamond films. So diamond-like carbon and vapor deposited diamond. So these are the two types of films that we are going to talk about. So in this course, we have actually not talked so much about diamond and diamond-related materials, mostly because you see a lot of research when it comes to carbon materials is more focused on graphite and graphite type, graphite-related materials. But indeed, there are certain diamond-related materials also that are very important industrially. Okay, for example, we use these synthetic diamond crystals in a lot of cutting tools and drilling tools. We also use diamond related films as heat sinks. So actually on your inside your computer in the circuitry, you might have heat sinks that are actually prepared by diamond like carbon films. So these diamond related materials are also important. So we are going to discuss also what are the applications, what is the difference between vapor deposited diamond and diamond like carbon. Why do we use these two different terms? And how can we actually get diamond when we are performing normal standard CVD? So CVD, actually also in the case of diamond CVD, you will use methane, similar sources, hydrocarbon sources, and they will get pyrolyzed, and then there will be certain form of carbon that is deposited. So what is it that gives you diamond and not graphite? Okay, so this is something that is very interesting. In fact, the mechanism of the formation of diamond is very interesting, and this is what we are going to discuss. So what are these diamond-like films? Well, they do not contain large diamond crystals. So large, by large I mean even microscale crystals are often not present. So what we have is nanoscale diamond crystals. Okay, now in some cases you will also find some sp2 carbon because well, during the CVD process you may end up getting some sp2 carbon, but typically what you would call vapor deposited diamond films will have a reasonably high fraction of sp3 or diamond type carbon. Okay, so this is the definition. Okay, now again, as I mentioned, we simply pyrolyze a hydrocarbon gas, and that is what we use as carbon source when we are using CVD or chemical vapor deposition. But there are also physical deposition methods. So this is what we are going to discuss now. What is interesting, and as I mentioned, that why should you not get graphite and why should you get diamond? That is the most important question when we are performing pyrolysis of a hydrocarbon, or even if we are using any other hydrocarbon source, so for example, or carbon source. So even if you're performing a physical vapor deposition, PVD, or you're performing chemical vapor deposition, ultimately you're getting some carbon species which are which are active and which get deposited onto a substrate, right? Now, the most thermodynamically stable form is graphite, which basically means that whenever you get this kind of atomic deposition of carbon, in principle, you should get graphite-like films. But what is it that induces the formation of this, sp3 type crystal and diamond-like films? Okay, so it turns out that the most important difference between the deposition mechanism of diamond and graphite is the presence of atomic hydrogen. Okay, so also when we were performing CVD of graphite or graphite-like materials, we often had hydrogen as the carrier gas, or it was mixed with methane when we were performing CVD. So also then you will say that yeah, there also we had hydrogen, here also we have hydrogen. So what is this something special about diamond formation? It turns out that in the case of graphite-related materials CVD, what you have is molecular hydrogen. Hydrogen does not really participate in your reaction. Okay, but in the case of diamond formation, what you must have is atomic hydrogen. That means when your H2 molecule splits into two H atoms, hydrogen atoms, and these are, of course, you can imagine they are highly reactive atoms. They form a certain link when the carbon film is forming. Then there is a certain link of hydrogen or stability that is provided by the hydrogen atoms, which is then which enables the formation of the 3D or sp3 type structure. So let's see, let's discuss this with the help of a diagram. Okay, so this is your diamond structure. Can you relate to it? So this here, these so this is your pyramid, right? So this is sp3 type hybridization. Okay, so you get some basic diamond film. You have this sp3 like structure. So you have this entire film, and now you see this is your pyramid. So this is the fourth bond. This, in the case of graphite, that is missing. So this is here we have the sp3 hybridization. So this is a sp3, fourth sp3 type orbital which goes up. Okay. Now you have this on top of all the pyramids. Okay. So this is your film number 1. Now if you did not have any atomic hydrogen, then what would happen is this structure would flatten out. So you will, because that is more thermodynamically stable form, so this structure would flatten out, and what you would get is a graphite-like film. However, if you do have the atomic hydrogen present, so this is another, by the way, this is another film. I have just shown it with a different color just to tell you that this is how you have, the growth in the Z direction of your diamond film. Okay, the atomic hydrogen, as you can see here, then that sort of facilitates some sort of stability. It goes and gets attached to these sp3 type, this is your fourth electron. Okay. Now, if you don't have hydrogen, then you will get graphite formation. But if you have the hydrogen, now you have this sort of intermediate structure. And later on, this hydrogen is then replaced, and then you get another film of diamond. So in order to maintain the sp3 type bonding, it is very important to have hydrogen there, and this is the special thing about CVD of diamond, and this is something that you don't have in the case of any graphite related materials. So atomic hydrogen is very important. So as I have mentioned here, this anchoring of hydrogen, that prevents the 111 planes of diamond from flattening. What are the 111 planes of diamond? So we have not discussed diamond crystal structure in much detail. This is, as I had mentioned, that you have two interpenetrating FCC type structures. This is the structure, it is in fact called the diamond crystal structure. Even also some other materials, for example, silicon also has this diamond type crystal structure. So what is this two interpenetrating FCCs? So here I have just shown a simple cube. Okay. Now on this cube, in the case of FCC, all faces have one central atom, right? So I have shown it with shown these atoms with a different color, but they are all equivalent, chemically equivalent. Okay, this is just for convenience I'm describing it. Okay, so you have these 6 atoms on all 6 faces of your cube. Okay, so now you have an FCC structure. Okay, now in the case of diamond, you will have these 4 additional atoms that sit inside your FCC. Okay, and these 4 additional atoms, they are bonded to 3 the atoms that are sitting on the centers of your face, and the 4th one which is on the corner of your cube. Okay, so that is your crystal structure. So I was saying, I was talking about 111 plane. So 111 plane, similar, you will take it similar to, you will take it for any other cube or cubic crystal. So this is your 111. Basically, it is this this diagonal plane, and it is the diagonal plane which when you see a diamond crystal grows, then that comes as a facet, and this facet will not exist. The structure will flatten out if you did not have the atomic hydrogen to bond with your 4th electron, which is of which would possess sp3 type hybridization. Okay, fine. Now you can imagine that even though you have this very reactive atomic hydrogen, it's not, there is always a possibility that some sp3 bonds, they are not anchored with hydrogen, and then you will immediately get some sp2 type carbon as well. And that is in fact, when we talk about the quality of the vapor deposited diamond films, the quality is actually, there are 2 things. Number one, how high is the fraction of sp3 type carbon compared to sp2, because this is then sp2 type carbon is kind of your impurity when it comes to diamond films. Okay, so that is number 1, and number 2, how much hydrogen impurity do you have in your films? Okay, so these are the 2 important things that determine the quality of your diamond like carbon, diamond vapor deposited diamond. Diamond like carbon is the carbon actually where you have a high fraction of sp2, and this is something we will talk later. Okay. So in any case, often there is some diamond, some graphite which is always formed in the process. Okay. Now, atomic hydrogen, as I also said, that this is also present as an impurity. But this atomic hydrogen, it is doing one more interesting thing. So it's not just the anchoring, it's not just the the facilitating the diamond formation. One more thing this atomic hydrogen does is that because it is highly reactive, atomic hydrogen, you can imagine that is very highly reactive. It is only formed above 2000 degrees centigrade. In fact, that is the reason that also makes our when it comes to the overall CVD process, the CVD is of diamond is different also in terms of the temperature at which, so pyrolysis of methane will already take place above 500-600 degrees, but unlike graphite CVD, you will go to very high temperatures, or if you're not able to go to very high temperatures, you will need some other source, for example plasma source, for the activation, for the creation of these hydrogen species. Okay, so the point is that this is when the hydrogen splits into its atomic form, this material is very highly reactive. So what it also does, that in the case of graphite, it etches graphite away. So you also, this is another mechanism by which the production of sp2 type carbon is reduced in the presence of hydrogen. Okay, so it is performing in two ways. It is increasing the production of diamond and reducing the production of graphite. Okay, as I mentioned already, so you can either have arc discharge or some sort of high energy plasma, then you can have your atomic hydrogen, or you have temperatures above 2000 degrees. Okay, or both. In many cases both. Fine. So there are a couple of methods that are used for the production of the CVD. So the CVD and PVD, when you are using arc discharge plasma, in that case you can also simply use a graphite source, and you don't really need to use methane or any other hydrocarbon as your carbon source. But when you're using a hydrocarbon as a carbon source, then you call it CVD. And when you just use graphite as the source, then it is called PVD, because there's no chemical reaction, so to say, taking place. But it is again, in the case of diamond CVD also, CVD, you can still use a lot of hydrocarbons. It doesn't have to be methane. It can also be benzene. It can also be so similar to any. See, hydrocarbons in our CVD processes are just a source of carbon, and that it's actually irrelevant what hydrocarbon you use, as long as you're able to get the carbon species that you desire. Okay, so you can use also again a number of hydrocarbon species. However, acetylene plays an important role in the case of diamond CVD. We'll come to it. Okay, one important thing is also that you don't really use any catalyst here. So unlike in the case of graphene, carbon nanotube, and all these graphene type materials, the catalyst was very important, and the solubility of your carbon atoms in your catalyst played an important role. But here that is not the case, because you do not really care about the solubility of carbon atoms. You just have a physical deposition of film. So often you will have silicon as a substrate. So substrate is basically just for the collection, and it does not perform any catalytic role in the process. Okay. One more important thing is that the substrate temperatures, so I've written typically below 900 degrees centigrade, maybe in some cases people can go above up to 1000 degrees centigrade, but it must be kept below 1000. And the reason for that is your diamond films are not very stable. Okay, so these nanoscale diamonds, that also depends on the exact crystallite size. But these diamond crystallites, they may actually start converting into graphite if you go above 1000 for sure, but even below 1000 if the crystallites are very small. So typically you will have the temperature between 700 and 900 degrees for the substrate. Fine. So yeah, hydrogen impurities are often observed. But one more interesting thing is that the presence of oxygen. So we often avoid presence of oxygen in the case of carbon production, right? But here the temperatures and the energy of the entire system is so high that even oxygen can convert into atomic oxygen. So there you're not really getting combustion here, but the presence of oxygen can also facilitate sometimes the anchoring. Even the presence of water can increase the rates of the CVD process, of the film deposition. The exact mechanism of why oxygen helps in this process. The exact mechanism is still being investigated. There are theories about it, but the idea is that the presence of oxygen, the presence of water also increases the rate of the film deposition in the case of diamond PVD as well as CVD. Okay, so now let us discuss a little bit more about the actual methods. So the setup that we use and how we perform this process. Okay, so I think I already mentioned that both PVD and CVD can be used for the deposition of diamond. In the case of PVD, we are basically using a graphite or any carbon target, and then we are removing the atoms from there. And of course, hydrogen needs to be present in both cases. So there are two necessary conditions. Number one, atomic hydrogen must be present. Otherwise, you will get graphite. Number two, even the carbon species need to be highly activated. So even the carbon species need to be provided some activation energy. Only then you will get these sp3 type carbon structures. Otherwise, as I mentioned, always graphite is thermodynamically favorable. So you will always, whenever there is a chance, the carbon will convert into graphite. Okay, so these are the two conditions. Now let's first talk about how do we perform the physical vapor deposition. Okay, so as this, I think I already mentioned that you do not use a hydrocarbon source. So you directly use a carbon target. So it is very similar to sputtering and evaporation that you perform also in the case of microfabrication. The idea, the only thing is that you have this hydrogen gas present and you also have plasma present. So plasma is the one that will actually split your hydrogen molecules into atomic hydrogen. So that energy is provided by very high energy plasma. Okay, so again, if you use hydrocarbon, it is CVD. If you just use a carbon or graphite target, then it is PVD. But plasma is present pretty much in all cases. Okay, so you can also call these, plasma enhanced CVD and plasma enhanced PVD processes. Okay, so anyway, the arc discharge is what creates the plasma or what generates the plasma, and this and also generates, by the way, the atomic carbon species. Okay, now this is a very high current density arc plasma. Okay, so that is even I think somewhere I will also describe the parameters. So this is the plasma itself is also, it contains very high energy, a very high intensity plasma because of high energy density, high current densities. Okay, fine. So this is where you're basically continuously providing the plasma, and that is something that is creating your hydrogen. Now this hydrogen formation from the molecular to atomic hydrogen formation, you can imagine that this is a very high energy process, right? It requires a lot of energy, and in fact it also is endothermic because it requires a lot of energy. It takes energy from the surroundings. The enthalpy of this reaction is actually 430 plus 434 kilojoule per mole. So you can imagine that this is a very energy consuming process. What also happens because of its endothermic nature of this reaction, it becomes very difficult to maintain a good temperature inside your CVD chamber. So you can imagine that there is so much energy that is, this reaction is already taking so much energy, so much heat. So there is fluctuation of heat, and that is why substrate is often separately heated using some sort of heating coil or something like that. So you have this very highly endothermic process going on inside your chamber. Okay, and if you miss out on your temperature control, then very easily you can get graphite formation. If the carbon species are not, they do not have high enough energy, or if you end up, not getting enough atomic hydrogen, or if your atomic hydrogen converts back to molecular hydrogen, because that is also because this is a very highly reactive species, and also the atomic hydrogen tends to immediately convert into molecular hydrogen, and once it is converted into molecular hydrogen, then this is kind of no use to us, right? So all of these things are indeed hard to control in this process. Okay, so now here I have shown basic schematic of a PVD setup. So you can see here the most important thing is that your arc vapor source. So you have a graphite target there, and the rest of the things, basically this is some sort of very simple electrical circuitry. You have two electrodes, and you have your substrate attached to one of your electrodes, which is your collector. you will typically rotate this entire, both your electrodes and substrate. The rotation is often done in a lot of sputtering CVD or evaporation type of methods, just because so that your entire substrate can get uniform films. Okay. So also then you have an exhaust for the flue gas and so on. So this is a very simple diamond PVD setup that I have shown here. Okay. Now we come to the CVD. Okay, so in the case of CVD, again you have carbon species, hydrogen species that are obtained by pyrolysis of a hydrocarbon. But again, they are both they are present in the when you also have the plasma. Okay, so both carbon and hydrogen species need to be activated at all times. Now you can use two types of plasma. One is of course with the arc discharge that we already talked about. You can also use RF plasma. You can use microwave plasma. Okay, so microwave plasma is non-isothermal, but the arc plasma is isothermal. So depending upon your process, you can use both types of plasma. Okay, so various organic precursors can be used, but most of them, it is at least believed, or the proposed mechanism suggests, which I'm going to show you on the next slide, that you have this CH3 radical or methyl radical that is formed, and then there is acetylene species that attaches to your this pyramid-like structure, and that is how the film deposition propagates. Okay, so this is one proposed mechanism. However, the idea is that irrespective of it, it doesn't matter what is your precursor, as long as you get these methyl radical. Okay, fine. So higher concentrations of methyl radicals, of course, will increase your deposition rate. So let's talk about the mechanism of CVD. Okay, so here I'm showing the mechanism, or one proposed mechanism, of the CVD of diamond. So here you see you have these 3 carbon atoms, right? So 3 carbon atoms are basically, these are the sp3 type carbon atoms, but you have the 4th one on top, which is also attached to this hydrogen atom. So you see there is one hydrogen atom that is anchored to your 3 carbon atoms. Okay, but you know that this is only an intermediate step. Right, so hydrogen is not going to stay there forever. In fact, this is just providing certain stability, and what happens is the next hydrogen atom comes there, and immediately hydrogen molecule is formed, because that is a thermodynamically favorable process reaction. Okay, so you will now have this C3 radical. So 3 carbon atoms in the shape of, let's say, pyramid, and the 4th one where you had the hydrogen, now the hydrogen is gone. So now what you have is a C3 radical. This C3 radical then gets, there is a 4th carbon atom that is required. Now that 4th carbon atom comes from the acetylene species present in the system. Now acetylene species can be present even if you did not use acetylene directly as your carbon source. So you can even use methane or benzene or anything else, and still you will have some acetylene species present. These radicals, or this species then connects to your, then gets attached to your carbon atom, and there you now have 4 carbons. Okay, now you have the sp3 type structure completed. So all the non-carbon atoms will then either cleave, or they will just stay in the system. That is why you also find some hydrogen present in your diamond-like films. But you typically, this is a mechanism of getting 4 carbons, or sp3 type framework to be formed. Okay. So there are actually some other mechanisms also that have been proposed, but this is something which has been experimentally verified multiple times, and that is why I have shown it here. Okay. Now let's come to the plasma. So as I said, that whether it is PVD process, CVD process, plasma is important because you see with plasma you can provide high energy for the hydrogen atomic hydrogen production without going into very high temperatures. So that is why often plasma is used. So there are 2 types of plasma, microwave plasma. Let's first talk about the parameters, as I mentioned before. So the operating microwave frequency typically is 2.45 gigahertz. Okay, and the incident power is about 600 watts. So you can imagine that 600 watt is a pretty high power for plasma. Okay, typical etching processes are performed at 50 watts and 50, 100 watts. So these are when you use it in microfabrication and so on. So this is a very high energy plasma, and it also has the very high electron density. So it's also the intensity of your plasma is very high, also because you have in 1 meter cube you have about over 1000 electrons. Okay, so it is a very high energy plasma. Okay, the idea is that you need all this high energy because you should be able to dissociate hydrogen, which is not a very common process. You can imagine it requires very high enthalpy and so on. Substrate temperature, as I already mentioned before, should be below 1000 degrees centigrade. Typically between 700 900 is the common temperature for substrates. Okay, you may have hot wall reactor if needed, but either way your substrate should be separately heated because of the temperature fluctuations. What is happening is this hydrogen dissociation is typically happening reasonably close to your substrate, and that would fluctuate the temperature also of the substrate. It should also not be too cold. So you cannot have substrate at room temperature. You can also you should not go above 1000, but also typically not below 700. So your substrate temperature, so substrate is often separately heated, and you also have separate thermal sensors to be able to note the temperature of your substrate. Okay, now the deposition rates for diamond films, especially if you want to get good quality diamond films, are actually reasonably slow, and it can even take several days to coat a certain substrate. So this is the entire thing. It's a so slow process. Okay. Now let's talk about the other type of plasma. So that is the arc plasma. So that is as the name itself suggests, it's created by an electric arc. This is a high intensity plasma as well, but low frequency. And then we create using either AC or DC. You can create the arc between two electrodes. Okay, so you have different types of cathodes and anodes, but typically the most commonly used ones are tungsten cathodes and copper anodes. And these electrodes are also often water cooled. Okay, so again you use methane. Similar to other CVD processes, you will dilute it in argon or any inert gas generally. Okay. Now what happens is this methane is supplied in a very narrow, there is one very sort of a small chamber inside the chamber where you have your arc present, and that is where you also need to supply your hydrocarbon source. So in a very small region, then you have this very high intensity arc, and the plasma is generated because of that. And substrate and electrode, everything where the temperature is maintained by both heating and water cooling, that because, and these kind of CVD setups, that is why they will have multiple valves, not just for different gases, but also for water jets for cooling. Okay, so even the plasma jet is sometimes cooled because you need to, so all of these things need to be cooled because you need to maintain the optimum temperature, both substrate as well as the reaction chamber. What you can also do is sometimes you need to increase the length of your arc. In that case you can or even sometimes the shape, you can make it a helical arc. So you play with the shape and size of your arc with the help of magnetic fields. So you can also have certain magnetic fields inside your CVD chamber. Okay, fine. What is also interesting is you can even obtain doped diamonds. For certain semiconductor applications, you can actually have boron or phosphorus doped diamonds. If you can mix these boron and phosphorus precursors inside your, with your methane gas, with your feed gas. Okay, so even that is possible. So these are the methods of producing diamond using CVD and PVD processes, but in all cases it is plasma enhanced. Okay, so what would be the optimization parameters? Of course, because you have the plasma, intensity of plasma is very important. Other than that, the usual things, temperature we already talked about, also the pressure in general, and the gas concentration, of course, because you have various gases, all of these things are your optimization parameters.